Hello friends, welcome. Friends, today we are going to talk about an important announcement which has been made by Mr. Elon Musk himself yesterday through a tweet. You see this tweet? This tweet is dated 17th June 2024. Right? So let's look at this tweet, what he's saying. In this tweet, he's saying that I just set it up right now. I'm writing a post using this space. And what is this space? This is a new Starlink Mini antenna, right? Which is looking something like this. Conventional antenna of Starlink. Starlink is what? Starlink is a satellite system which provides internet connectivity to the user using that system. And that internet connectivity is not being provided through conventional way, which is optical fiber or terrestrial system. They are provided through a satellite based system. For that you need this antenna. Now conventional antennas of Starlink are of larger size, which is typically around, the length of that antenna will be around half a meter. Now this antenna is almost like half the size. And I'm going to show you how much is the size difference. So if I go to the Starlink's antenna specification, this is the antenna, the conventional antenna, this is the antenna. And this antenna, if you go down below, and you will see that this antenna is, the size of the antenna is mentioned here, 513 millimeter by 303 millimeter, which is how much? It is 51.3 centimeter to 30.3 centimeter. So this is the size of the antenna. Now if I come here and look at the size of this antenna, which is being mentioned here, is what? 28.9 centimeter multiplied by 24.8 centimeter, which is, you can say it's almost like half, which makes this antenna portable. Means you can carry this antenna anywhere, wherever you want. And the other main difference between this antenna, the antenna which I just showed you here, this one, versus the antenna which is being mentioned in the tweet of Mr. Musk, is that the Wi-Fi capability of the system is integrated into this portable antenna versus the antenna where Wi-Fi router is different. Why it is different? Because the Wi-Fi router has to be located inside the house, and this antenna which you see here, this antenna is located outside the house, maybe on the rooftop. So there has to be a cable which emanates out of this antenna. The cable will come out and it will go and connect to a router which will be inside the house. Whereas if you look at this particular tweet, you will see that this antenna has got an inbuilt Wi-Fi router, and therefore you don't require an external router. So two advantages of this particular system. One advantage is what? It is miniaturized, and therefore you can carry whenever you want, and you don't have to put a separate Wi-Fi router, and you don't have to connect any cable outside to get your Wi-Fi connectivity in your computer or whatever device that you are using. Now why I am doing this video today? The reason I am doing this video is to explain to the viewers that what are the limitations of a satellite system. Whenever we talk about any communication, futuristic communication, people tend to believe that technology has the capability to bring stars from the sky into the hands of the users. Okay, that's the perception. Means anything and everything is possible in this world, right? It is just a matter of time, right? But no, because as you have, those who understand physics or maybe at least have heard about something about physics might know about Mr. Einstein. He was the most, I would say, the biggest physicist of the century. He had created a relativity theory where he said that the speed of light is constant anywhere you go in the universe. Now, I don't think that anybody will come out with a concept or a technology if it is going to break this physical limits of speed of light, the way the speed of light functions. Similarly, technology always will have a limitation. Technology is not going to solve each and every problem that you may encounter in your life. purpose of this video today is to explain to you the limitation of a satellite technology and how, with this invention or this deployment of the new antenna which I am talking about, how the overall system capability is going to get compromised, because nobody is going to talk to you about this issue, that how the overall limitation of the system is going to get compromised. The reason I'm saying this is that if you look at Elon Musk's tweet, he has also uploaded a speed test result, which is what he's saying. The speed test of this antenna which he is being using to write this tweet says that the antenna has the capability to download 100 Mbps. This is what he is saying, and upload speed he's getting around 11.5 Mbps of upload. Now friends, will you compare, what I'm basically trying to say is that will this, if you compare with a conventional Starlink antenna which is of this kind, and then you start using this antenna which Elon Musk has recently tweeted in his tweet, will those two antenna will give you comparable speeds of data, both upload and download? Because the speeds may vary depending upon what situation you are in. Maybe you are in a congested situation, you may not be able to get the proper elevation of the satellite or the visibility of the satellite. Maybe there is some interference which you are seeing. So you need to do apples to apples comparison to measure whether these two systems are going to give comparable speeds or not, and what is the main reason for that difference. That will give you an insight of a satellite system, and also tell you that satellite system can never emulate a conventional terrestrial system. People may be talking about this, they don't need BTSs. Like for example, there was a recent article about the Chinese scientists developing the first orbit that allows smartphones to make direct calls, satellite calls, where people have been talking. I've seen so many video people are saying we don't require any BTS now, we'll just live with satellite. Never going to happen like that. And today's video I'm going to explain to you why it is not going to happen like that. You will never have a satellite system replacing the complete terrestrial system. So there are two objectives of this video. One is to compare this system with the conventional system, which is right here, which I showed you here, and the reason for the difference in performance. So for that, what I have done is I have created this presentation. Now, because anything and everything has to be compared based on some mathematical equations, means you can't simply make any comparison based on heuristic assumptions. You have to compare based on physics and mathematics. But to the viewers who do not have any understanding of physics, I would simply say that don't get overwhelmed by these equations. These are very simple equations, and these may not be applicable under real practical situation where these equations might require to be tweaked. So I am not making any claims that these are the equations which are absolutely going to be applicable under the real life situation where their capability might change or may get improved. But since I am using a reference equation to do the comparison for both situations, if you do an apples to apple comparison, situation may remain same, which is the ratio may not change. That's the whole purpose of this exercise. Now, there are two important points to make comparison with. The first is the antenna gain, right? The gain of the antenna. And why this gain of the antenna is very, very important, we will understand this as I go through this video. What is the gain? What purpose that it serves? And another is the beamwidth impact. So here is the beamwidth impact. What is the purpose of beamwidth? And what purpose it serves, and how it makes the system more robust and there has limitations. So we're going to talk about both of this. So let's now talk about antenna gain. Now, in order for you to understand antenna gain, I am going to take you through a diagram. What is this diagram? This diagram shows a satellite. You can see a satellite on the sky. This is the satellite. And this satellite is talking to this ground antenna terminal. Now, both satellite as well as the antenna has been blown out of proportion. Don't be overwhelmed by that. Just consider a satellite hanging in the sky and there is a ground terminal talking to the satellite. Now when this both this system talk to each other, they send RF signals. The radio frequency signals will be sent by the satellite, and this receiver is going to receive this signal. Now when the radio signal comes and hits this antenna which is on the ground, this signal will get amplified. There are two ways to amplify the system: using physical electronics, which will be inside the equipment right here. Another is the form factor of the antenna that will help in delivering that gain, and this is going to be depend on the dimension of the antenna, and therefore it is going to be important for you to consider that. So when you talk about dimension, it also, the frequency of the RF signal also plays a very important part, and that is the reason why I have this equation in front of us. So what it says, the gain of the receiving antenna, which is right here, you see the gain of the receiving antenna can be represented by the equation pi. Pi is just a constant, just forget about it. Pi is just a constant. Then we have the diameter of the antenna, which you saw here, right here, diameter of the antenna. And then lambda. Lambda is the wavelength, which has got direct relationship with the frequency. Means frequency is related to wavelength. How it is related to wavelength? If you know the velocity of light, then frequency is the velocity of light is the product of frequency f multiplied by lambda, right? This is the equation, which means in order for you to calculate lambda, what you have to do? You have to divide the frequency the velocity of light by frequency. So that's how you calculate lambda. So what you do is that you just give a square of this term and multiply it by the antenna efficiency. So once you do that calculation for conventional Starlink normal disc antenna of, let's say, this size of 0.5 meters, we have just simplified it. It may not be accurately 0.5 because the antenna is not circular in nature, it is rectangular in nature, right? That's what we saw. But for simplicity, I am making this assumption as a diameter of 0.5. So when you do the calculation and you substitute 3.14, which is pi, multiplied by 0.5, which is this, then multiplied by lambda, which is divide by lambda, which is 0.024 for a frequency which is roughly around let's say 14 gigahertz, 14 gigahertz or 15 gigahertz, in the range which satellite operates, and then you multiply by the efficiency of the antenna, you get a term which is called gain of 3229, which is the conventional normal disc size of antenna, right? This is the gain. Now if you are going to use the mini disc size antenna, which is size of 0.5 meter of diameter, you get a gain of how much? Antenna gain of 997. So the ratio comes out to be around 3.3. Now if you are going to have a gain of this antenna, which of the conventional antenna, which is higher by the mini antenna by 3.3 times, which means that if you are going to use a mini antenna here versus a conventional Starlink antenna, which I just showed you for doing this reception, your signal is going to get deteriorated or get throttled by a factor of 3.3. Correct? That's how it is. Now if your signal strength is going to get reduced by 3.3, then your signal to noise ratio is going to get compromised by that factor, right? That's very simple, because in order for you to understand the signal, it has to be above the noise level, because if it goes down the noise level, that signal will get mixed with the noise and you will never be able to extrapolate the signal, right? So you have to have your signal higher than the background noise level. There will be some noise which you will see in the background. Your signal has to be higher than the background noise level. Simple as that. Now you see that a conventional antenna of Starlink of a larger disc size is going to give you a better gain of 3.3, and the mini antenna which we saw here in this tweet of Elon Musk right here, and that mini antenna has a size which is less and is going to give you a gain which is going to be less. So therefore what is going to happen? Well, this is going to make the system what? So let's do the data rate estimation using these values. So now let's assume that you have a 500 megahertz of signal, 500 megahertz of bandwidth. Right? The bandwidth can be 500 megahertz, it can be 1 gigahertz, but for the sake of simplicity, I have taken 500 megahertz. I can use 1 gigahertz also. Now, because the signal to noise ratio in case of the mini disc is going to be lower by factor of 3.3, then what will happen is your efficiency of modulation that you will be typically using, and I've just assumed an efficiency of 2 bits per hertz. Now, this is again a technical thing. You don't have to get overwhelmed by this term called 2 bits per hertz. What it basically saying is, let's say if you have got 100 mbps, 100 megahertz of bandwidth, then the throughput that you get within that block of spectrum is determined by the bit rate which you can transmit within that bandwidth. Bit rate is what? That is the carrier rate, means the carrier frequency. Now the carrier frequency determined, it is being directly impacted by the modulation rate. Now the modulation rate is impacted by the signal to noise ratio. Means if the signal to noise ratio is high, you can use a better modulation rate. But if the signal to noise ratio is low, then you can't use a better modulation rate. You have to use a lower modulation rate. So for the mini disc, therefore I have assumed a lower modulation rate of 2 bits per hertz. And therefore I am getting a data rate of maximum throughput within that bandwidth of 500 megahertz of 1 Gbps. Similarly, Starlink's normal antenna, I have assumed a modulation scheme with a bit rate of 3 bits per hertz. That will give you a data speed of around 1.5 Gbps or 1500 Mbps. Which means that if you are going to make a comparison between these two systems, just because of the form factor, your throughput is going to get reduced by 33.33%. Right? Because this is the equation. Again, I don't want to get into all these equations because these are technical terminologies which is going to confuse the shit out of the whole thing. Let's not look into the technology part or the technical part. Let's look at simply. Let me summarize. You have a certain bandwidth on which you are transmitting certain RF signal. Now the throughput within that particular bandwidth is determined by the modulation scheme. The modulation scheme can be higher or lower. Now if your signal to noise ratio is lower, you can't use a higher modulation scheme. You have to use a modulation scheme which is going to be lower. That is why I have used 2 bits per hertz, because as you saw that the gain of this mini disc system is lower by 3.3 times compared to the Starlink ordinary terminal system. That's how this calculation has come. 100 1000 Mbps of throughput within that bandwidth of 500 megahertz, and this is going to be 1.5 Gbps or 1500 Mbps. That is why that there is going to be a direct reduction of 33% if you take all other consideration alike. Right? That is why this is going to be get impacted by that. So you will never get the same throughput which you are going to get in a conventional system using normal Starlink terminal. That is the compromise which you have to make if you want to make the system more mobile. Now come to the beamwidth impact. Now beamwidth impact is what? This satellite which you are basically pointing towards, your ability to connect to this satellite determined by the thickness of the beam, because this RF signal will have a certain thickness, and that thickness is the beam width. Beam width means that the beam can be narrow, it can be wide depending upon the frequency at which you are using as well as the disc form factor. If you are going to have a wide beam, then your ability to track the satellite is going to be better, because you don't have to point very narrowly to the satellite. Your accuracy of pointing to the satellite may not be that accurate, and still you will be able to catch the satellite if your beam width is going to be wide. But if the beam is going to be narrow, then your accuracy of catching the satellite is going to get decreased significantly, because you have to then align the this particular station in such a way that it points to the satellite accurately. Means you can't really have any compromise on the installation of the terminal on ground. That's why beam width is important. So higher beam width means that you may be able to live with a lower installation quality. Lower beam width means that you have to live with a higher install. You can't compromise on the installation on ground. So let's compare these two things, right, using the formula. Now, if I use a conventional formula, you will see to calculate beam width. Again, I am not going to get into the formulas. You will see that for conventional Starlink system, it comes out to be around 3 degree. Whereas for the mini disc, it comes out to be around 5.45 degree, right? What is degree? 90 degree is like this, right? This is 90 degree. Now you can make the comparison. What is 3 degree and what is going to be 5.45 degrees. So the mini disc has got a higher beam width, which means that the mini disc can be deployed on ground with a very marginal kind of installation requirement. You can just place it on ground. You don't require a very high directed deployment installation requirement. Whereas for the conventional system with a higher disk size, you require a sharper installation requirement on ground because the beam width is narrow. But there is a compromise that you have to make, and that's why it is very important, and I'm repeating this again and again. Lower beam width means that you will be able to manage interference better, because what will happen is that your terminals are going to be your Starlink terminals who has a narrow beam width will be more precise and focused toward the satellite, and therefore reducing interference and improving pointing accuracy. However, if you have got a higher beam width, then this particular system will be more prone to interference. That is another reason why you will not get a better data rate for mini disc. You understand why the mini disc is going to compromise on data speeds, throughput, versus having that opportunity of full mobility or carrying on your backpack and taking anywhere else. Now, why I'm emphasizing on this particular point? You can clearly see that in order for you to get a reliable system, a satellite system, you need the satellite system installed on ground with a higher disk size. The disk diameter has to be higher, because that will enhance your gain as well as make the beam narrower, which will make your data throughput much higher compared to a mobile system. Now, mobile system has to be of a smaller size, his beam width will be higher because his diameter is going to be lower. That is where the problem comes, that we are going to face, and this compromise we have to live with. And now comes the important point of consideration. Now imagine a mobile phone instead of this particular terminal that we spoke about right now in our discussion. This is the Elon Musk new thing. Let's say that it's miniaturized further and gets converted into a mobile phone form factor. Can you imagine the kind of constraints that you're going to face? Because the size is going to get further reduced, and you will not have the luxury of placing the device on ground for aligning with the satellite. You will carry that device on your hand. So there is no way you will be able to get any meaningful data comparable to even the mini discs that which you are going to carry in your backpack. So that's where the point of discussion is, which I am leading towards, that satellite providing connectivity to the mobiles, right? If you look at this particular diagram again, let me bring this diagram on ground. If you see this mobile handset, right? And this mobile handset is talking to the satellite. Now you will never be, this mobile handset is talking to the base station. You will never be able to have a mobile handset here talking to the satellite directly, because of the reasons which I have explained to you, that the form factor is going to be so low that your gain is going to be extremely low, your SNR is going to be very, very low, just marginal level of noise, your data speeds are going to be very low, because you will have to use a bit rate which is going to be very low, you can't use a higher coding mechanism, your throughput is going to go down significantly, and therefore you will never be able to use data properly using a conventional mobile. And therefore, for you to get reasonable speed for conventional mobile, you have to use a terrestrial system. You can't live without a terrestrial system. Satellite will never be able to provide data connectivity comparable to what terrestrial system will be able to provide using a conventional mobile system, right? So that's the point about this discussion. The other issue is that because this whole system is highly dependent on SNR, and your throughput depends upon the bit rate at which you are transmitting. If you are going to transmit at a higher bit rate using a satellite system, then what is going to happen is that your bits or the frames, which the information which is getting transmitted to the satellite, are going to be more prone to errors. Means you may need to drop the packets, means you need to ask for retransmission from the satellite system. Now, if this distance is going to be 600 kilometers, imagine that this distance is 600 kilometers, and you are recalling or asking for retransmission again and again using in the satellite system, the kind of latency that you're going to add to the overall system versus a conventional mobile system where the base station may be 5 kilometers apart and it can ask for retransmission again and again. Therefore, it has got the luxury to use a coding mechanism or a coding system with a higher throughput. So your bit rate is going to be much higher within the bandwidth, equivalent bandwidth, if you compare these two systems apples to apples. Because you don't have to. Even if you are asking for retransmission, this is only a 5 kilometers or maximum 10 kilometers versus 600 kilometers, which is going to make the latency much more manageable in a conventional mobile system versus a satellite system where 1200 kilometers has to be traversed, because sending the request up and then bringing the request down, because the 600, let's assume the satellite has 600 kilometers of height, 1200 kilometers have to be traveled, and as I told you, the speed of light is constant, which is basically same as RF signals also emulate speed of light, which is 3 lakh kilometers per second. So you will have that kind of latency. You can do your own calculation, you will be able to understand. That is the reason why FCC has, if you look at this particular document, and FCC has clearly said in this document, you just go through this document, this is a recent document, and I'm going to show you this is an order of review. So what Elon Musk wanted, his company Starlink wanted, is to be given USO subsidy, which we typically give in case of our conventional systems to be deployed in rural areas. So they wanted USO subsidy, and they are asked for subsidy to be provided terminals in rural areas in the US system. So they have bid for auction, and they have basically requested FCC to grant that approval. Now what FCC has said in this order, and I can share the link also in the description of this video. So if you go down below and if you read through this particular order, FCC has made very, very stringent comment. So what it says, if I go down below, and let's wait for a minute, and I'm going to point out to the important. So what it is saying, after reviewing all information submitted by Starlink, the Bureau ultimately concludes that Starlink has not shown that it is reasonably capable of fulfilling the requirements to deploy a scope and scale size of the requirement. This is one. And then if you go down below, which I marked with red, just a minute, where is it? Yeah. It says that after careful review, we find that the Bureau followed the Commission's guidance. Bureau means which has reviewed the earlier application of Starlink and correctly concluded that Starlink is not reasonably capable of offering the high-speed, low-latency services throughout the area where it won auction support. It won auction supports. That's why the claim of Starlink to get the USO subsidy was rejected. So this is a typical problem with satellite system. It is very, very unreliable, and therefore these systems are only to be used in areas where there is no terrestrial connectivity, and these are such systems which are so prized, because if you look at the conventional antenna of Starlink, not the mini antenna, it costs you around $500, and this is going to maybe cost you around $250. Still, it is going to be very, very costly. And the service price, there is no way to know what the service price would be, because typically they charge for the normal service, for Starlink conventional service, $100 to $150 per month, which you can imagine for Indian rupees, it is going to be 16,000 rupees per month. Can you imagine that? Even if it is reduced to a level 50% or 25%, still it is going to be 4,000, 5,000 rupees per month. Nobody can afford. So anyway, so I'm going to stop here. I just wanted you to understand this new thing which came up, and it kind of got to my notice, so I did this video to make you understand this. So I hope that you found this video useful, and let me know in the comment section if you have any comments or suggestions. And look what this commission is saying. Commission was generally skeptical about LEO satellite system meeting download upload speed requirement in any tier. As a result, the Bureau imperceptibly applied the heightened scrutiny to Starlink long form application. We disagree. That's what he's saying, right? Anyway, so I'm going to stop here, and I hope that you like this video, and let me know your comments, and I'll come back with a new video next time. Thank you very much.